Hey, computer science principals. Um, Today I'm just going to have you go through some lessons, finishing up chapter 2, and going through this video and going through some of these slides. And we're going to talk about, you can take some notes as well. Um, and so that's it. So we're going to go and talk about yesterday. Yesterday, you had to, you went through the internet simulator and kind of found that when you're communicating information to another person, that information is broken up into small chunks called packets. And those packets sometimes are routed differently, and sometimes those packets are lost. And so depending on what information we are sending, we either didn't really care if we sent them out and the receiver got them in a different order, or we came up with rules to make sure that it was very accurate. So this is kind of where we left off. The first challenge that you had with the internet simulator was simply just sending a message to your partner. And you didn't really care if you didn't really follow your protocol. You didn't follow any rules for sending. You just sent out the message, and if you didn't even check if they got it. This example, or that example would be similar to the protocol of UDP that the internet does use occasionally. It's called User Datagram Protocol. You can just remember it as UDP. And the basics of how UDP works is just that you're sending information to someone else, but you don't really care if the packets arrive perfectly. You're simply sending out the packets and hoping that they get to the receiver. And that's it. You don't go through any checking to make sure things are in the proper order. There's no communication between the sender and receiver that much besides just sending it, but there's no back and forth. Okay, so some examples in real life. This would be a good protocol to use for like video streaming, because let's say, if you were streaming the Super Bowl and that was being broadcast from a certain source, then you might have millions of people that are watching or streaming from a certain source, and that source is just sending out bits to different locations. It's basically just being broadcast. It's just shooting out this information, and the users or the people that are receiving the stream are not going back and forth between the host who's streaming it and error checking every single bit that's coming across and making sure and asking back and forth between those two computers. That would be way too slow. And you'd have millions of people trying to check and error check with like some video stream. Well, you can't really do that in video broadcasting, or it would be painfully slow. So UDP is a really good protocol for that. You just send it out, and you're really not going back and forth and error checking. The second thing that you did was came up with rules and protocols to make sure that your message came accurately. This would be an example of TCP that the computer uses, or Transmission Control Protocol. And the basics of how this works is really what you did in your activity. You have all your packets that you're going to send, and you send them out, and there's a back and forth communication, possibly to resend any packets that were lost. And then you will also number the packets so that the receiver who gets them can put them back in the correct order that they were meant to be in. And there could be multiple back and forth communications between the sender and receiver. So this is useful when you're doing everyday things, obviously, especially when you need accuracy. So like sending an email, photo, going to websites, especially where text is involved, then you are always using TCP. So in general, you should just know that these are two different protocols that the internet uses for sending information. Most of your everyday things is using TCP. But if you're streaming from video, you might be using UDP, where back and forth communication is not always there. Okay, so UDP is faster, but not necessarily as accurate. TCP is accurate, and it could be slower, although you don't really notice in your everyday things. You don't really notice the slow back and forth communication there because things happen so quickly. Okay, so I want you to watch this video. It sort of wraps up all the things we were talking about in yesterday's lesson.
7, 6, 5, 4, 3, 2, 1.
Hi, my name is Lynn Root. I am a software engineer here at Spotify, and I will be the first to admit that I often take for granted the reliability of the internet. The sheer amount of information zooming around the internet is astonishing. How is it possible for every piece of data to be delivered to you reliably? Say you want to play a song from Spotify. It seems like your computer connects directly to Spotify's servers, and Spotify sends you a song on a direct, dedicated line. But actually, that's not how the internet works. If the internet were made of direct, dedicated connections, it would be impossible to keep things working as millions of users join, especially since there is no guarantee that every wire and computer is working all the time. Instead, data travels on the internet in a much less direct fashion.
Many years ago, in the early 1970s, my partner Bob Kahn and I began working on the design of what we now call the internet. Bob and I had the responsibility and the opportunity to design the internet's protocols and its architecture. So we persisted in participating in the internet's growth and evolution for all of this time up to and including the present. The way information gets transferred from one computer to another is pretty interesting. It need not follow a fixed path. In fact, your path may change in the midst of a computer-to-computer conversation. Information on the internet goes from one computer to another in what we call a packet of information. And a packet travels from one place to another on the internet a lot like how you might get from one place to another in a car. Depending on traffic congestion or road conditions, you might choose or be forced to take a different route to get to the same place each time you travel. And just as you can transport all sorts of stuff inside a car, many kinds of digital information can be sent with IP packets, but there are some limits. What if, for example, you need to move a space shuttle from where it was built to where it will be launched? The shuttle won't fit in one truck, so it needs to be broken down into pieces, transported using a fleet of trucks. They could all take different routes and might get to the destination at different times, but once all the pieces are there, you can reassemble the pieces into the complete shuttle and it'll be ready for launch. On the internet, the details work similarly. If you have a very large image that you want to send to a friend or upload to a website, that image might be made up of tens of millions of bits or ones and zeros, too many to send along in one packet. Since it's data on a computer, the computer sending the image can quickly break it into hundreds or even thousands of smaller parts called packets. Unlike cars or trucks, these packets don't have drivers and they don't choose their route. Each packet has the internet address of where it came from and where it's going. Special computers on the internet called routers act like traffic managers to keep the packets moving through the networks smoothly. If one route is congested, individual packets may travel different routes through the internet, and they may arrive at the destination at slightly different times or even out of order.
So let's talk about how this works. As part of the Internet Protocol, every router keeps track of multiple paths for sending packets, and it chooses the cheapest available path for each piece of data based on destination IP address for the packet. Cheapest in this case doesn't mean cost, but time and non-technical factors such as politics and relationships between companies. Often the best route for data to travel isn't necessarily the most direct. Having options for paths makes the network fault tolerant, which means the network can keep sending packets even if something goes horribly wrong. This is the basis for a key principle of the internet, reliability. Now, what if you want to request some data and not everything is delivered? Say you want to listen to a song. How can you be 100% sure all the data will be delivered so the song plays perfectly? Introducing your new best friend TCP, Transmission Control Protocol. TCP manages the sending and receiving of all your data as packets. Think of it like a guaranteed mail service. When you request a song on your device, Spotify sends a song broken up into many packets. When your packets arrive, TCP does a full inventory and sends back acknowledgments of each packet received. If all packets are there, TCP signs for your delivery and you're done. If TCP finds some packets are missing, it won't sign. Otherwise, your song wouldn't sound as good, or portions of the song could be missing. For each missing or incomplete packet, Spotify will resend them. Once TCP verifies the delivery of many packets for that one song request, your song will start to play. What's great about the TCP and router systems is they're scalable. They can work with 8 devices or 8 billion devices. In fact, because of these principles of fault tolerance and redundancy, the more routers we add, the more reliable the internet becomes. What's also great is we can grow and scale the internet without interrupting service for anybody using it.
The internet is made of hundreds of thousands of networks and billions of computers and devices connected physically. These different systems that make up the internet connect to each other, communicate with each other, and work together because of agreed upon standards for how data is sent around on the internet. Computing devices, or routers along the internet, help all the packets make their way to the destination where they're reassembled if necessary in order. This happens billions of times a day, whether you and others are sending an email, visiting a web page, doing a video chat, using a mobile app, or when sensors or devices on the internet talk to each other.
All right, so after that video, just here are some vocab terms that you should be familiar with. Especially, I'll point out the really important ones. So packet, you should know what a packet is. Packet is a chunk of data sent over the network, and just knowing that when you have something to send, everything is broken up into packets, into small chunks. Those packets could be out of order, and TCP, if you go over here to TCP, the Transmission Control Protocol, that kind of goes along with these packets, and as the video kind of pointed out, that's a protocol for sending packets that does all the error checking to make sure all the packets have arrived, and if there is missing packets, that it sends it back, some messages to get those packets. UDP that we talked about is a protocol where it's less strict. There's going to be no error checking at all, or I guess we could say minimal error checking, but we're just sending packets and we just really don't care about the missing packets. We don't care about if they're out of order. We're just sending it, and both parties kind of know that ahead of time. Two things that we didn't talk as much about: packet metadata. Metadata is always, it's data about the data, right? So if I'm sending some information to someone else, like a photo, packet metadata might be the IP address that it's going to, and it might be the IP address that it's coming from. It's not part of the, it's not part of the photo, but the packet metadata helps to go to the correct location, and it's needed, right? The packet metadata would be like the to and from on your simulator. Data stream, information passed through the internet in packets. So just a data stream, right? It's like you're sending information. Okay, so that kind of wraps up yesterday's lesson. Now we are going to talk about DNS and HTTP, and that will take us all the way through today. So, question to you is, if I was in class and I had to and I gave you my phone, could you call one of your friends? So the prompt was, think of one of your friends right now. If I gave you my phone, could you call them? And the answer is, for a lot of you, no, because you don't remember their number, right? You have something that remembers that for you, and it maps those numbers to, maps those names that you have stored in your phone to an actual number. Okay, same thing happens with websites. So these IP addresses, right? If you were, these IP addresses actually will go to certain computers on the internet, right? So this is YouTube. I'm going to try some of these really quick. And if I go in the URL bar and I type this in, that actually just brought me to Google. So that actually makes sense because YouTube is owned by Google. But you can try some of these as well if you want. Just copy and paste some of these IP addresses and see where it takes you. So that first one, the first one was Google again. I guess everything owns Google, or everything is owned by Google. That second one took you to Apple, for example. So this is an IP address of an Apple computer, or something that's serving the Apple website at least. So of course you're not going to remember, right? You're not going to say, I'm going to go to Apple today. Let me just pull out let me just remember this number, 17.178.96.59, right? In order for you to communicate and get information from that website, you have to communicate to this IP address or this computer. However, we don't do that. We use a domain name. We just say apple.com, and somewhere in the middle there, it knows to go to this number, right? So that is a system of DNS, a domain name system or a domain name server. Okay. So if we want the internet to scale up to billions of devices, we need a better way to figure out another person's IP address. So I'm going to go ahead and show you some stuff about IP addresses and DNS now. And again, you can watch.
IP address.
Most users never see or care about internet addresses. A system called the Domain Name System, or DNS, associates names like www.example.com with the corresponding addresses. Your computer uses the DNS to look up domain names and get the associated IP address, which is used to connect your computer to the destination on the internet.
And it goes a little something like this.
Hey, hi there. I want to go to www.code.org.
Yeah, I don't know the IP address for that domain. Let me ask around. Hey, you know how to get to code.org?
Yeah, I got it right here. It's 174.129.14.120.
Oh, okay, great, thanks. Yeah, I'm gonna write that down and save it for later in case I need it. Hey, here's that address you wanted.
Awesome, thank you.
So how do we design a system for billions of devices to find any one of billions of different websites? There is no way one DNS server can handle all the requests from all devices. The answer is that DNS servers are connected in a distributed hierarchy and are divided into zones, splitting up responsibility for the major domains, such as .org, .com, .net, etc. DNS was originally created to be an open and public communication protocol for government and educational institutions. Because of its openness, DNS is susceptible to cyber attacks. An example attack is DNS spoofing. That's when a hacker taps into a DNS server and changes it to match a domain name with the wrong IP address. This lets the attacker send people to an imposter website. If this happens to you, you are vulnerable for more problems because you are using that fake website as if it is real. The internet is huge and getting bigger every day, but the domain name system and internet protocol are designed to scale, no matter how much the internet grows. IP address.
All right. So now, if I was in class, we would go to the last and final version of the Internet Simulator. And that Internet Simulator would take you, again, through sending messages to your partner and trying to communicate to your partner. I'm not going to say that you have to go through it. I would say if you have some time to go ahead and connect it, if you and someone else want to give it a go. It is, I'll essentially just kind of talk about what it does. instead of, yesterday you had a partner and you said, hey, what's your IP address? And then they told you it was like 5.2. I'm on router 5 and I'm computer 2. If there was no talking at all, and I said, all right, go ahead and communicate with someone or communicate with one of your friends, then you could ask the DNS server. The DNS is basically just telling you what the IP addresses are and managing all the names and all the IP addresses that you have. So if you know, the name of a computer, you can ask the DNS server, and what you would do there is you would say get, and then you would have the username of your friend or your partner, which could be on the same router. And you'd say get username, and it would send back what the IP address of that person is. Once you have the IP address, then you could just communicate as normal. And that's essentially all it is. So the DNS server, the DNS system is extremely important because it allows us to not have to type in numbers. And I can simply type in www.espn.com. And again, when I type that in, it's not going directly to ESPN server. It's first going to a DNS server and figuring out what the number is, right? Once I get the IP address, then once I know, then I can go ahead and send information to and from, and I have that number as necessary. So again, DNS, super important. You should know what that is, domain name system. All right, what else do we need to go through today? I'm just kind of going quickly over this. I know there's a lot of vocab, there's a lot of videos and stuff like that. The last protocol that you should be familiar with is HTTP. HTTP stands for Hypertext Transfer Protocol. And it's yet another protocol for sending information, and specifically web pages. So I'm going to play this video again on HTTP and HTML. If you've created websites or if you've taken web design, then this stuff might look a little bit familiar. Okay. Of course, if you go to any website as well, all your websites technically start with http:// and then I go to some sort of website after that. That HTTP is a protocol for getting information from an actual website. Okay, so think, browsing websites, things like that. So I'm gonna go ahead and play the video. Questions that you should be thinking about. What is HTTP? What is it? What problem is it trying to solve? What is a GET request? And what are you requesting? How does HTTP rely on the other layers of the internet? And then, why are SSL, TLS, and HTTPS necessary? Now, you're not going to have to know exactly the details of these protocols, but you should know that it's a group of protocols that are different than the others. All right, so let me play it.
I'm Jasmine Lawrence, and I'm a program manager on the Xbox One engineering team. One of our biggest features is called Xbox Live. It's an online service that connects gamers from all around the world, and we rely on the internet to make that happen. This is no easy task, and there are a lot of things happening behind the scenes. The internet is totally changing how people interact and connect. But how does it work? How do the computers all across the world actually communicate with each other? Let's look at web browsing. First, you open a web browser. It's the app you use to access the web pages. Next, you type in the web address, or URL, which stands for Uniform Resource Locator, of the website you want to visit, like tumblr.com.
Hi, I'm David Karp, the founder of Tumblr, and we're here today to talk about how those web browsers we use every day actually work. So you've probably wondered what actually happens when you type an address into your web browser and then hit enter. And it really is about as crazy as you can imagine. So in that moment, your computer starts talking to another computer called a server that's usually thousands of miles away. And in milliseconds, your computer asks that server for a website, and that server starts to talk back to your computer in a language called HTTP. And HTTP stands for Hypertext Transfer Protocol. And you can kind of think of it as the language that one computer uses to ask another computer for a document. And it's actually really pretty straightforward. If you were to intercept the conversation between your computer and a web server on the internet, it's mainly made up of something called GET requests. And those are really very simply the word GET and then the name of the document that you're requesting. So if you're trying to log into Tumblr and load our login page, all you're doing is sending a GET request to Tumblr's server that says get/login. And that tells Tumblr server that you want all of the HTML code for the Tumblr login page. So HTML stands for Hypertext Markup Language. And you can think of that as the language that you use to tell a web browser how to make a page look. So if you think about something like Wikipedia, which is really just a big, simple document, and HTML is the language that you use to make that title big and bold, to make the font the right font, to link certain text to certain other pages, to make some text bold, to make some text italic, to put an image in the middle of the page, to align the image to the right, to align the image to the left.
The text of a web page is included directly in the HTML, but other parts, images or videos, are separate files with their own URLs that need to be requested. The browser sends separate HTTP requests for each of these and displays them as they arrive. If a web page has a lot of different images, each of them causes a separate HTTP request, and the page loads slower. Now, sometimes when you browse the web, you're not just requesting pages with GET requests. Sometimes you send information, like when you fill out a form or type a search query. Your browser sends this information in plain text to the web server using an HTTP POST request.
So let's say you log into Tumblr. Well, the first thing you do is you make a POST request. That is a post to Tumblr's login page that has some data attached to it. It has your email address. It has your password. That goes to Tumblr's server. Tumblr's server figures out that, okay, you're David. It sends a web page back to your browser that says, success, logged in as David. But along with that web page, it also attaches a little bit of invisible cookie data that your browser sees and knows to save. And that's really important because it's really the only way that a website can remember who you are. And all that cookie data really is an ID card for Tumblr. It's a number that identifies you as David. And your web browser holds on to that number. And then the next time you refresh Tumblr, the next time you go to tumblr.com, your web browser knows to automatically attach that ID number with the request that it sends over to Tumblr server. So now Tumblr server sees the request coming from your browser, sees the ID number, and knows, okay, this is a request from David.
Now, the internet is completely open. All of its connections are shared, and information is sent in plain text. This makes it possible for hackers to snoop on any personal information that you send over the internet. But safe websites prevent this by asking your web browser to communicate on a secure channel using something called Secure Sockets Layer and its successor, Transport Layer Security. You can think of SSL and TLS as a layer of security wrapped around your communications to protect them from snooping or tampering. SSL and TLS are active when you see the little lock that appears in your browser address bar next to the HTTPS. The HTTPS protocols ensure that your HTTP requests are secure and protected. When a website asks your browser to engage in a secure connection, it first provides a digital certificate, which is like an official ID card, proving that it's the website it claims to be. Digital certificates are published by certificate authorities, which are trusted entities that verify the identities of websites and issue certificates for them, just like a government can issue IDs or passports. Now, if a website tries to start a secure connection without a properly issued digital certificate, your browser will warn you That's the basics of web browsing, the part of the internet we see day to day. To summarize, HTTP and DNS manage the sending and receiving of HTML, media files, or anything on the web. What makes this possible under the hood are TCP/IP and router networks that break down and transport information in small packets. Those packets themselves are made up of binary, sequences of ones and zeros that are physically sent through electric wires, fiber optic cables, and wireless networks. Fortunately, once you've learned how one layer of the internet works, you can rely on it without remembering all the details. And we can trust that all those layers will work together to successfully deliver information at scale and with reliability.
All right, so that explained how HTTP and HTML work, right? So there are a lot of layers now that a lot of terminology that is going on here. And you're not going to have to know super in detail what each, like what SSL is or TLS, like what is going down, how that's working in intricate detail. You just have to know how the layers of the internet rely upon each other and what their basic functions are. So some key takeaways from this lesson: scalability. Scalability is the capacity for the system to change in size and scale to meet new demands. So if something is scalable, it's really easy to, add more routers, add more computers, make the system bigger without too much trouble. DNS, you should absolutely know what that is, and that is the system responsible for translating domain names, like example.com, into numbers or IP addresses. HTTP, right, is Hypertext Transfer Protocol, and that is a system for getting documents or getting web pages, HTML documents, or other resources when you're web browsing. And so what else do we have here? The World Wide Web, www, is physical from the internet, is different from the internet. The World Wide Web are files, web pages, media. The internet is the network we use to access those files. Okay, so what you should be able to do with all of this to kind of wrap up all this terminology, how the internet works, is understand the layers of the internet. Okay, so if you click on this little activity here or this little guide, this will be very helpful when you are looking through and reviewing exactly what all of these vocab words and ideas mean. So, layers of the internet, kind of as the video described, in this little picture up here describes, is that you have kind of a higher level layer, and then you have lower and lower and lower levels or layers of dependency. Right? We already know the lowest level. We already understand how bits work, right? How binary works. And then from there, IP addresses. We know how IP addresses work, right? Every computer needs to have a number so that you can talk to a specific computer and you can send these bits across. Now, as you go up from that, what is TCP and UDP we talked about today? That's a system of, taking data and putting it into packets and having those packets ensure that they are received and sent properly, right? So then you have this layer up here that's managing the sending of data. And then on top of that, if you're on a web browser, okay, and you are transmitting web pages or HTML, then you have a system of HTTP and DNS, which is on top of these layers. So in general, you should go through these things, understand what each layer or what each protocol does and how it works and how these things rely upon each other to get something done. For example, if I go to a website and I just go to google.com or gmail.com, you should be able to explain to me what happens in all these layers and how they work together. So if I go to google.com, I'm using HTTP request to get the web page, google.com. The DNS server is helping me get to the correct IP address because I don't know what the number is, so the DNS helps me out there. The TCP and UDP break up my messages and communication into packets and make sure that all those packets are arrived and they arrive on time and everything is there. And that is relying upon the IP layer, right? The internet protocol we are depending on, and we know that the server we're talking to has an IP address that we can talk to, and all this information is really being brought down into bits, ones and zeros, which is then transferred, on a physical network. These bits and ones and zeros are then sent over back and forth between these computers. Okay, so you should use this kind of as a study guide. Understand what these terms are and understand how the layers of the internet work together.